Okay, so let's consider chemical reaction or the phase transformation process. So we will have some idea what is the driving force and what is the inertia of the system. So this is a chemical reaction. Reactant A react with reactant B, then we will generate or produce product C and D. So if you draw the diagram of free energy, gives free energy versus the reaction coordinate, then you can divide it into 3 stages. The first stage is reactant A, so you just simply sum up the free energy of A and B, and as long as it can overcome this energy barrier or activation energy, then you can get or produce the product C and D. And based on this diagram, we can have some idea about what the reaction directions. Because the Gibbs free energy at the stage 3 here is smaller than here. So the delta G is the total system energy of the system is decreased after your reaction, right? So based on this, delta G is negative. So we can say, based on the thermodynamics, the direction of this chemical reaction is going to go to right. The direction is to right. But this is a driving force, right? And what's the system of inertia? So what's the energy barrier or activation energy here? Because thermodynamics just tell you, oh yes, this chemical reaction happens. But the thermodynamics didn't tell you how fast this chemical reaction is. So that was depending on the activation energy. And this is some kind of similar to like the one we just mentioned is the system or inertia of the system. So as long as the activation energy is small, then that would be the kinetics favorable. That means you can speed up the chemical reaction. Okay, so this is this driving force part we can predict by thermodynamics, but this part, system of inertia, something like that, that will be involve the kinetics process.
More about the kinetics. So before so what's the kinetics? Actually, is the rate of the state function evolution. So before, as you know, thermodynamic equilibrium conditions defined by thermodynamics, actually the state function do not change with time. But here, kinetics, actually the state function did change, and we do care about the rate of the state function evolution. And the state function here usually we choose will be the free energy. For diffusion in solid materials, probably is a Gibbs free energy or the entropy. These two state function. And the rate of state function evolution may involve the change of shape, size, composition, or crystal structure of materials. And we need to calculate the rate of state function change, no matter is the Gibbs free energy or entropy. But some people probably have some concern about the all energy state function we derive from thermodynamics is only can be applied in the equilibrium conditions. Why we can apply this energy state function in kinetics? Yes. If you want to apply this energy state function in kinetics, we need to make some assumption. So here in our textbook, we call it is we make assumption. What kind of assumption we make is we assume our system is local thermodynamic equilibrium in this our interesting kinetics process. So what's the local thermodynamic equilibrium? So let me explain it that if we put a metal bar, this is at constant temperature T0. So we believe when you plot the temperature profile versus the location, the curve will be like this, right? It's T0. However, so this is under the thermodynamic equilibrium condition, right? The state function do not change with time, unless temperature along this metal bar are the same. And how about if I ended a heater here, then ended a cooler here, cooler. How about how the temperature profile changes over time? In the beginning, probably it will be like this, right? Let me enlarge this one. So in the beginning, probably it was like the temperature here probably is slightly, probably go this way, because at the left-handed, the temperature will be increased, and at the right-handed, the temperature will be decreased. And after a while, when the heat Q in from the heater and the Q out went out of the system, when the Q in equals to Q out, then we are going to observe the temperature profile will go this way, and this will be Tc, this will be the Th. Because Q in equals to Q out, so let's know the accumulation of heat flux along this metal bar. So this temperature profile, this slope, this profile do not change over time, right? And this will be reach the steady state. And this is what we are talking about in kinetics. Will be reach the steady state, and the temperature profile do not change over time. So if we focus on this location, probably is here. This temperature, what's the does this temperature change over time? No. So this is what we call is the local thermodynamic equilibrium, because the state function T at this location, this local location, do not change over time. But if you look through a whole metal bar, yes, the temperature profile everywhere, temperature along this metal bar is not the same with this. Actually, is at the left-handed is Th and the right-handed is Tc, right? But if we look local, no matter it's like if you look this point location and the temperature profile, the temperature at this location is this value, but because it's steady state, this profile do not change over time. So at this local site, the temperature do not change with time. Actually, this definition is similar with the equilibrium condition. So this we call is a local thermodynamic equilibrium because it's a thermodynamic equilibrium at a local microscale site. So based on this assumption, we can apply all the energy function derived in thermodynamics to kinetics process. So this is a quite important assumption. So this is very important. This is very important assumption here. Otherwise, we cannot just directly use all the laws or state functions derived from thermodynamics in kinetics process.
Okay. If we just put a material in the system, and usually it is like equilibrium condition, right? Thermodynamic equilibrium condition. So we need to apply a force to put these materials or put these systems, push this system to deviated equilibrium state, then allow these systems move from deviated equilibrium state to equilibrium state, and what kind of path it chooses and the corresponding rate will be the kinetics process. And what parameters will affect the rate of this state function changes? So that will depending on two important parameters. The first one is the driving force applied on the system. So we need to consider the magnitude and the time period of the driving force applied on our systems. And the second one will be the inertia or mobility of the system. So I will give you 3 examples. So what's the, just some note, what's the mobility? Is when we apply the unit force, then the velocity of the atom move. What's the velocity of the atom? And also, we can give you examples. For example, like the trunk versus a sports car. If we use the same engine in trunk and also the sports car to drive the trunk and sports car, then which one run faster? The sports car should run faster, right? Why? Because we use the same engine with the same horsepower, so the driving force applied on trunk and sports car are the same. However, the inertia of the system of trunk and sports car are different. This one is lighter, this one is heavy, right? So based on the same driving force, the lighter one will run faster. So in kinetics process, we need to find out what is the driving force and what's the inertia of the system. So I'll give you 3 examples and hope you can figure out what is the driving force and what is the inertia of the system. The first one is the melting process. Melting process, that means we have solid materials, and after dissolving the heat, then this material is going to become a liquid form. So you can see like the structure randomized. So what's the driving force in this case? You can consider the entropy increase can be a driving force. And what's the inertia of the system? Would be what? Would be the material property, depending on what kind of melting process we are talking about. If it is a water melting process, then because the melting process should be structure randomized, that will involve the mass transport, right? So the diffusivity. of your interesting material would be dominant key point, will be the dominated key point or parameters. So the inertia of the system will be involve the material property. And what's the creep? Creep means the atomic diffusion under a stress field. So you can use a light to hang up a metal bar. And after like a couple years, then we can find that this metal bar get longer and longer. And this phenomenon, we call it a creep. And the driving force will be the stress field or stress gradient applied on these materials because we use a light to hang it up, right? And this stress field will drive the mass transport of the atoms, and the purpose will be minimize the system free energy. And you can observe it get longer and longer, and the strength increase over time. And what's the system of inertia in this case? That would be because atomic diffusion means the mass transport, right? So the inertia of the system would be the diffusivity of these materials. So for example, like diffusivity, the diffusivity of diffusivity changes with crystal structure. For example, like FCC, BCC, HCP, the atoms, the diffusivity of the atom to go through the FCC, BCC, HCP will vary, will be different. And also, the atom moves through the grain or through the grain boundary definitely is different. So the diffusivity would be the inertia of the system or of the material here. And the third one is the grain growth. Grain growth, what's the grain growth? That means grain growth, that means actually the material you have first, it will be the polycrystalline materials. And you put your polycrystalline film into the furnace and heat it up. Then you can observe the size of grain get bigger and bigger, and the number of a grain decrease. And in the meantime, you can also observe the total volume of a grain boundary decrease. So at this moment, you will know the total grain boundary energy decrease. Then the purpose also to minimize the system free energy. So the driving force probably is the grain boundary energy, and the system of inertia of the system also will be the diffusivity because it involves the mass transport or diffusion. So it will be the diffusivity path or diffusivity of these atoms. Okay, so next slide. So I already give you some examples for some kinetics process, and hope you can easily find out what's the driving force and what's the inertia of the system. Both of these will affect the rate of the kinetics process. And next slide is going to talk more about the driving force. As we know, the driving force is proportional to the degree of the deviation from the equilibrium state. So let's take this as an example. If we have a blue ball, you put it at the floor, the base floor, then you can consider that if we don't touch it, then this blue ball is at the equilibrium state. Then now I push this blue ball along this slope and reach this higher level. And this blue ball have potential energy equals to mgh against the gravity, right? So when I release this blue ball is going to move from deviated state toward to equilibrium state to minimize the system energy. So this is the driving force. So usually in the beginning, the material system is in the equilibrium state, and we will apply a driving force to push it to the deviated state, then reduce it, then it's going to be back to the equilibrium state. And the magnitude of a driving force is related to the degree of deviation from the equilibrium means. If I push the blue ball to this height, it's higher than this, right? So this blue ball is going to have a higher potential energy. So when I release this blue ball, the driving force much larger than this one. So this means the driving force is proportional to the degree of deviation from the equilibrium state. And in this case, it's easy to calculate the driving force here, right? Because you just take the gradient of the internal energy. The potential energy, the potential energy. Then take a gradient of it. So just divide it by the distance, then you can get the driving force applied here. So the driving force is proportional to the potential energy of the blue ball. Okay, so the other thing is I give you an example. Another example is a phase transformation. Then we can talk more about the energy barrier or the system inertia part. So this case is we also have a graph of free energy G versus the reaction coordinate. Then this reaction is alpha converted to beta phase. And we also have, based on the thermodynamics, we can observe this reaction definitely happen because alpha converted to beta, the delta G is negative. And how fast it happens depending on the activation energy or the energy barrier here, right? So the rate of this phase transformation is determined by what? The driving force first, and also the transport resistance, or you can call it as energy barrier. And just a remark here, mobility is proportional to with the inner system inertia, right? Okay, so back to this case, alpha converted to beta. So maybe let's say example talking about a diamond and graphite. Probably you heard about that before. Diamond actually is at the 1 atm and room temperature. It is a metastable state. You can consider as here. And graphite is the most stable state for carbon atoms, so it can be here. So based on the energy difference, the diamond should convert it to graphite, right? Yes. In thermodynamics, yes. Finally, all the diamonds should convert it to graphite because the graphite with the lowest free energy of the carbon. But however, based on the thermodynamics, it doesn't tell you how fast this happens. So why we don't see our diamond ray converted to graphite? Because this energy barrier or activation energy is pretty high. So the high energy barrier for transformation from diamond to graphite, so it's quite difficult to us. In our whole life, we can observe our diamond ray converted to graphite. So we need kinetics to help us to identify how fast this reaction happens, and how to control or manipulate the rate in kinetics process. So we provided two options. The first one is either you can lower the activation energy. So by adding a catalyst in your systems, you provided the other path to the reactants to allow it converted to beta. So it's created the other path with a lower activation energy to allow the reactant converted to the product. Or you can increase the working temperature to allow more atoms can overcome the energy barrier. So the figure will be like this. The vertical axis is a fraction of a molecule. The horizontal will be the kinetics energy. So at a low temperature, we can know the majority of atoms have this amount of energy. When we increase the working temperature or environment temperature, you can observe this curve shifts. That means the more atoms have this energy. So if we don't want to change the activation energy or energy barrier of our chemical reaction, so by increasing the temperature, we can observe the rest of the number of atoms which can overcome energy barrier is larger than at the lower temperature. So for this one, you just allow more atoms, more reactants can possess higher energy to overcome energy barrier. Then you can speed up the reactions. Okay, and regarding to the driving force here, you can use either the temperature gradient, electrical field, or the chemical potential gradient to drive these reactions. Doesn't matter, but the purpose definitely is decrease the total free energy of the system. Okay, so let's so almost we finish all the. You have basic knowledge about what's the difference between the kinetics and thermodynamics, and how can we manipulate the kinetics process, and how to speed it up or how to slow it down. But in this slide, we are going to show you some special cases, because all the kinetics process sometimes is not a single step process. Probably is in series process or a parallel process. So you need to consider that. For example, like now we have ice ball, and when we put the small ice ball in the thermal isolated container, and the other one is we have a larger ice ball and also put in the container but without any thermal isolation. And after the same time period, we can observe the small ice ball one, you can still have some ice ball immersed in the water. But in this case, we only observe the water exists in our container. So this is tell you what, if we don't consider the environment settings and the boundary conditions, if you just focus on the size of the ice ball, probably you will guess this one will convert it to water, no ice ball. This one probably it will be some ice ball and immersed in water. But however, the results doesn't look like that you expected. So let's tell you this every kinetics process you need to determine whether it is series process or parallel process or just single step process. In this case, the ice need to absorb the heat, then can convert it to and transform to water. So that's a two-step. The first one will be what? Thermal transport. Then will be mass transport, the atomic transport, diffusion. Then can convert it to water. So when we have a series process, the slowest one will dominate everything. So here, in this case, obviously, the rate of ice melting is determined by what? By thermal transport, not determined by the atomic transport or diffusion. Okay, so I will give you a short summary of kinetics. Consider the time-dependent state change process for a system out of equilibrium. You need to pay attention about which path you choose and the corresponding rate. And don't forget, the kinetics is a time-dependent state function change process. And what factors affect the kinetics process? The first one will be the driving force. And the driving force can be what? Temperature gradient, electrical field, or what? Chemical potential gradient. And the other will be the system of inertia, or inertia of a system, or the transport resistance. These two parameters will affect the rate of kinetics process. And the third one is just give you some information, just a remind about the atoms, the thermally activated process, how you can estimate how many atoms with certain amount of energy will obey this explanation functions. Is some kind of a Arrhenius distribution, right? Okay, so you can estimate like exponential minus delta E is energy barrier over kT. So this is when we have a thermally activated process, then we can have some concept how many atoms do have certain amount of energy. We can use this explanation functions to have a roughly estimation on this. And regarding to the rate determining process, the first of all we need to determine your interesting process is a single step process, a series process like the melting or the solidification. You need to absorb energy, then you can do something, and then it's a mass transport, something like that. Or it's a parallel process. Parallel process is something like the catalyst process. You add some catalyst in your system, so you provide the reactant the other path with lower energy barrier to try to speed up these chemical reactions. Okay, so today we finished the first part. So that's ended here. So take home message would be like you need to, so far I hope you have some idea about what's the thermodynamics, what's the difference between the thermodynamics and kinetics. Thermodynamics gives some reference coordinate of the equilibrium conditions of a system, and kinetics give you some, how you, based on what kind of path you choose, then you can roughly give us the rate, corresponding rate, reaction rate of this path you choose or of these reactions. So kinetics is a time-dependent state function change process. And the rate of this kinetics process will be affected by the driving force, which we can predict. The driving force and the system inertia of the system. And also, when you deal with the kinetics process, don't forget you need to know which one is the rate determination process. It's a single process or serial process or parallel process. You need to have some idea about that, so you can easily calculate rate for this kinetics process. Okay, so today let's end it here.